So welcome to day 2. I hope you're all becoming more extroverted. So the laptop clearly got started prompt off on that. But so it's a pleasure to have Mirrokni from Google Research, and Vahab has done a lot of amazing work on applying like algorithmic ideas to problems at scale. And he also leads a really amazing team of researchers at Google New York. So he will tell us more about how to scale ML efficiency.
Thank you. Yeah, I'm going to talk about ML efficiency problems, a topic that's very related to the workshop here. But before that, I want to tell you the story of how we are moving to like solving the problems that we're solving now. As Sesh said, like I like lead a couple of teams in the Google Research New York and elsewhere for algorithm optimization. We have a large-scale graph mining project that's like a large-scale data mining project tool set for the rest of Google. We do large-scale optimization and market algorithms. And like the interplay between theory and practice, system, ML, algorithm, and economics is like what we do. We try to publish and also have internal impact, and that has been like very rewarding over time. The list of research topics is like large, but what I'm going to actually tell you about is how we have moved now in the past 2 years from basically large-scale algorithmic tools that we have built to optimizing for first like ML models and now more and more LLMs. Before I start and go deeper, I should just say that for example, this graph mining project, we have 4 pieces of this library. Some of it is based on like internal Google distributed hash table service and also like Flume models that can handle trillions of edges in a matter of hours. And then like we have a library that handles graphs with up to basically hundreds of billions of edges, maybe tens of billions of nodes, but on a single machine in a multi-core way in minutes or seconds. And we have a library under TensorFlow integrated with basically the rest of deep mining, deep learning work like graph neural networks, TFGNN, and another internal tool for dynamic graph mining. And this is what basically empowered us to have impact at Google, publish papers, and like be in touch with the academic community. The past 2 years, we have moved from using this graph mining library to also basically do like data mining for generative AI, and in particular at Google in the Gemini large big model that we are building. So internally, we have this nickname GM for the library, and now people like folks on the team are saying now we can use it for Gemini mining as well. So what I want to tell you is, yeah, algorithms and scalability remain critical when we move and are moving to generative AI and LLMs, what we call Gemini era at Google. So in 2023, we started looking more into how we can contribute to this space. And these are the areas that we identified as like very important algorithmic and scalability areas that we can contribute. The first and most important part is data quality and data curation at scale. Things like algorithmic tools like LSH, deduping itself, hierarchical clustering, different types of clustering algorithms, if used properly, are critical to improving different basically capabilities of these large models. For example, in the context of like algorithmic problems, data selection and data discovery is very important, both for efficiency, because when you want to build small models that are very efficient, it's very important to choose the right data, which is also very relevant to the capabilities that we want the LLM to have, and also diverse enough that we don't have redundancy in the model. So this is actually a dense slide in terms of what I'm talking about, but I don't have like good slides to elaborate on it, so listen carefully. The also other thing is that different type of capabilities that these LLMs should have. For example, even in math and reasoning. I remember talking to some of the folks working in this area at Google like 1.5 years ago, 2 years ago, and basically the question was how to add reasoning, or how good are these LLMs in reasoning, and so on. So one message, at least, that there is a school of thought that says, for now, these are so powerful models that, and we don't understand them enough, that like in order to add different type of reasoning capability, there is a lot to explore in how to feed the right data to these models to improve their capabilities. And that's, yeah, like has been like on the agenda in general. So, and then the algorithmic problems of making these large models more efficient, both from training and serving perspective, are very important, super important. The question of how well they can reason on algorithmic problems like graph algorithms, something that's very close to our heart, is an important question. And like we have explored these, we have papers now on this. The question of what is the mechanism design and like economics problems in the context of LLMs is an important algorithmic and auction related question. And we have some work on this, and so on and so forth. Also for safety and alignment, there are like very fundamental algorithmic questions. So I want to encourage everyone at the workshop and the algorithm community to work more and more in these areas because it's super important. So now what I'm going to tell you about is subset selection is a problem that I've been trying to solve at scale at Google. I want to tell you like a story of which parts of these have become more useful in the context of both data selection and also feature selection or model optimization for large models. Then I will put some time to talk about these sketching techniques that are very important in developing linear transformers or linear attention in the context of larger scale, like large language models. We have a number of work in this area, HyperAttention, PolySketchFormer, and that's very close to the topic of the workshop. So for subset selection, before I dive into the context and like some of the specific results, we have used subset selection as a whole in the context of both model optimization when we do feature selection, and also in the context of data efficiency and batch, or adaptive optimization of the models. Like let's call it like the active learning, basically. We have written many papers, and I can tell you that only a handful of these papers have been like really useful for us in practice. So, or in the other, like, we have this thing saying like we have like theoretical papers that try to explain practice, and they're interesting and like we appreciate them and so on. But when you want to explain something, you do it. Like you find the corner of the problem to basically find the right, like one way of explaining. What I have been trying to do more and more is to see like where we can develop theory that we can inform practice. And I can tell you that, for example, these two papers, or like maybe like this new also paper on subset selection, has been like really informing practice because we have implemented these and they beat like all the other interesting theoretical and like algorithmic results that we had. So I'm going to focus on the papers that inform practice and also more recent papers here. So why did I start working on subset selection problem? In general, because it's related to submodular optimization. And for people who know me, that's like very close to my heart, understanding how we can optimize a set function that has diminishing return property. Like in general, when you have Oracle access to it, but very efficiently and in a way that's useful for data efficiency and also model efficiency. So this is something that many of us know. Like if you haven't seen submodular functions, you have seen for sure the coverage problem, which is basically if you have like a graph, you want to select a subset of nodes, then when you look at the neighborhood of those nodes, you cover a large portion of the graph. We can have also a family set family system, and you want to choose a subset of k subsets that maximizes the cardinality of the union. So in diverse sampling for data selection, this becomes like very handy, like very important, because when we want to choose which subset of basically data to feed into a model. Diversity is important. In addition to this type of subset selection, clustering and like distance-based clustering, k-center, k-means, k-median, is also like very handy, like and relevant. Talking about the applications in the context of feature engineering, and I'll elaborate on this further. Is like many of these models, especially actually the embedding models, the models that have like a wide like embedding. They are not as deep as like LLMs, but they are large, let's say, embedding models. Feature engineering is super important to build a very efficient model. I mean, I do think that even for LLMs, feature engineering is important when you want to develop like a efficient LLM, but that's like more controversial. We have to discuss it further. But yeah, so this is the context in which we can look at different type of feature crosses, for example, that we can add to the model and make the model higher quality without increasing the size of the model. And that becomes like a larger scale set function optimization that we can model also as a submodular optimization. And like I'll tell you about sequential attention technique that helped us actually solve this type of problem. Yes? So like when, okay, like when you want to build like a model, like you want to keep track of which features are active for each input. And like that helps you put like a specific basically structure on your network. Like we can have a head for your model related to each feature cross. And what is a feature cross? It's like basically having two types of features, like a young student in Seattle. So like putting these feature crosses, if they become like important, and adding them to the model is very essential in building like a shallow but still very effective and like high quality model. Maybe that much I can say.
It would not be as efficient to train it, or the network has to become too big?
Yeah, so basically, but then like the way you can think about it is that which feature crosses we should activate, because if we have like so many combinations of feature crosses that we can put here, and that becomes a large scale subset selection problem. Even matrix sparsification, believe it or not, and I will be in trouble maybe if I say a lot more on this, can be formalized as a subset selection problem, because we have to decide which entries in a matrix to sparsify. Or if it's like a block sparsification, we put some structure also. We want to see which blocks of entries to sparsify. And when it comes to sparsifying or structure sparsity and for neural networks, yeah, the linear algebraic techniques are useful, but still, like when we have a neural network that we don't understand, it's like an oracle that we can actually search for the right, basically sparsity structure in that network. And that becomes a combinatorial optimization problem that has to be sublinear, because each oracle call is very, very expensive. So this is just to give you a sense of the applications. Now, let me talk about some of the techniques and some of the papers more directly, if I know how I'm doing. I guess this was an important intro that I wanted to do. Now I'll be having fun here. So like one technique that has been useful for us is what we call randomized composable corsets, to distribute the data in a way that we can solve the problem separately on each machine and then find the corset on each and then solve on the union of corsets. And that has become useful starting from this paper from PODES with Sepide, Piotr, and Mohammed, and then like moving it to what we call randomized composable corsets, and then like more recently what we call LSH-based composable corsets that also like divide the data also very fast, but using like an LSH technique or like a sketching technique to decide where we send each piece of data. Just to give you a sense, for example, even the coverage optimization, which uses like a sketching-based composable corset technique, we applied it to feature selection, and this can work very well in looking at millions, like hundreds of millions of different type of feature crosses, and optimize, find like a subset of feature crosses that can basically work very well for some embedding models. So one thing that I have to emphasize and summarize here is that, yeah, I looked at these problems from submodular points of view, but then over time, the question in my mind has been, is this submodularity assumption too strong or not? The question of selecting, for example, a subset of features or selecting a subset of data points that when we feed to the model or when we use in the model, the quality of the model increases, or the AUC of the model is optimized. Can that problem be solved in polynomial time and with a good approximation? That turned out to be like a surprising revelation for me, which basically says that the functions, the AUC functions that we are trying to optimize, not in like very basically full generality, even like for linear type models or generalized linear models, the problems are actually not like approximable when you want to really solve the original problem. So whenever we make a submodularity assumption for these problems, we are like moving away from basically the problem at hand. We need to understand what are the assumptions that make the real AUC function submodular. Yeah, there are some papers there, but I'm not convinced that we understand the reasons behind. So, and we know that, for example, submodularity does not hold at the very beginning. So there are some supermodularity basically behavior at the beginning for both what I call representative selection and also feature selection. So on the representative selection area, we looked at, for example, trying to solve the problem end-to-end using a graph neural network, which basically is completely like an end-to-end heuristic to solve this problem that's not solvable in, with a good approximation. And like we showed that like when we look at the whole problem, the clustering problem, and then the quality of the model in an end-to-end way, and then back propagate to the way of doing the like representative selection, it can improve the quality of the model by a good margin. It's a heavy solution. We can only apply it to models that are not too big, but it can actually give us basically better quality. So now I want to tell you specifically about the sensitivity sampling work that we did recently. It's going to appear in ICML. In many of these data selection problems, we are combining two ideas. One is what we call an importance score or marginal value score for the model that we have to take into account. And then the other thing is the diversity of the diversity of the points that we feed into the model. So this is the paper that's going to appear in ICML. It's combining diversity and margin sampling. The general idea here is that for small models, margin score may be useful. So we can keep sampling the points that have marginal value, better marginal value, and that's a submodular function. That's like maybe a basically reasonable approach. But do I have? Yeah. For huge models like LLMs, we can't be doing that. We have to have a combination of diversity and margin sampling. The question is, can we develop like a theory of like our understanding of how can we combine diversity and importance sampling? And that's what we do in this paper. The goal is to find a subset of data here that we can somehow show that the average gradient on this subset is similar to the average gradient of the whole data. So we formalize it with basically by looking at specifically the loss function that we are trying to optimize and the amount of loss that we have on a subset. Then we make a big important assumption that we can validate on data. The assumption that we make is that we have an embedding space that resembles basically the loss function of the model. And like we say that there's a Lipschitz condition that says if two points are close to each other in this embedding space, their impact on the loss for the model is also within some factor, that lambda factor. And now, but then we don't make this assumption in the worst case. We make this assumption on average case, so it's a weaker assumption. And that's something that we can actually verify on data, that on average, we can find embedding models with it's like a distillation technique here now. We build a model that can embed the whole data, but then we use it for diversity. So this is also validated on data. The technique at the end of the day is summarized here, what we call sensitivity sampling. We have the embedding space, so we do a k-means clustering, and then what we do, I guess maybe the next slide describe it better. So we do a k-means clustering, and then we look at the value of each center of these clusters. And then from there on, the way we do sampling is what we call sensitivity sampling. Sensitivity sampling is the sum of the distance to the center and the marginal value of that center. More specifically, this is the so one thing we can do now is end-to-end. With that assumption, we can show that we can get a loss that's 1 over square root of k of the best thing, but we have also the cost of the k-means as part of the basically the loss function here. Also, we also look at how this method really helps, like LLM sampling, and we show that it beats both diversity and also combining this diversity idea and the margin sampling, which is also very efficient, is really giving us marginal value here. So this is an area that can be explored more, both theoretically and empirically. We are exploring it more empirically. We also have comparisons now to what they call ask LLM. So you can also ask an LLM if this is a good training data point to add to your model. So we see that we can combine an ask LLM technique and the diversity in a similar way and improve, and so on and so forth. So that was about generally data selection. Now I want to tell you about this sequential attention technique for feature selection. The executive summary slide here is that we have a sequential attention type algorithm that search on the space of, let's say, feature crosses, or maybe more generally, parts of the matrix that you want to sparsify. We do it in an adaptive way and inspired by the attention mechanism, which is basically an exponential scoring on the priority of sampling the next point. And the interesting thing is that for models regression model, simple models, we can provably show that this technique is the same as the orthogonal matching pursuit and the lasso. So it has theoretical analysis, but the more complex the model or the neural deep learning model is, the better this technique works compared to the existing literature, because it's very adaptive and also very efficient. I guess the general idea here is to search for the best feature crosses in an adaptive way, but also at the same time in an efficient way. So when we want to explore which feature crosses to add, we can just keep adding them and then reevaluate or reconstruct the network, do hyperparameter tuning on the network as well, and then decide, okay, what's the next best feature cross to add? That's a combinatorial. So when we add a feature cross, we have to re-optimize the network. It takes a couple of days or whatever. So that's not efficient. What we do here is we keep track of a priority queue we call attention score. And instead of building basically the model from scratch, we only backpropagate one level to update the sequential, the attention scores when we add a feature cross. That gives us a lot of flexibility and efficiency in this search algorithm. And the interesting thing is that we applied it for feature selection, but now we are also applying it even for block metric sparsification, which is a paper that we just put on arXiv, and it has too much animation. We actually try to combine. Basically, now we are putting this idea of a sequential attention score on top of different type of combinatorial search type algorithm, like local search, greedy, and like round-robin optimization of the moves that we can make in optimizing the network. And if I want to move to my linear attention thing, I guess I have to skip this pretty much. But I'll show you, yeah, this is what I added last week under the impression that I'm going to give a 1-hour talk. So, so this is basically, there is this ACDC type algorithm that basically have been explored. And like we combine that idea, which is a round-robin optimization of the moves for sparsification and the sequential attention, and we beat it. Believe me, like there is also like a paper on arXiv. This space also can benefit from more theoretical understanding, and like we can change the algorithm and go back and like try it and see like if it works well. It's like a line of work that can help us really improve. I can't finish the talk before talking about at least fast transformers here. It's like very related to the topic of the workshop. So when I started looking at LLM optimization and all of this was the beginning of 2023. The most fascinating mathematical sketching problem out there in the LLM space was the complexity of the attention layer. So the story here is that the attention as it's implemented is a quadratic time, and that's like quadratic time as a function of the length of the context for the LLMs. And soon after we started looking at this with Raj, I guess like we had like some observation that the problem actually is not only quadratic time. It's not possible to crack, like to get a sub-quadratic time algorithm, but then we observed the paper on arXiv by Josh and co-authors. So it turns out that this recent work shows that you cannot achieve sub-quadratic time in the worst case. So now the question is, can we improve like by making some assumptions on the on the metrics, or relaxing the softmax assumption? Because the hardness results only apply when we have like softmax attention metrics. And like the story here is that the HyperAttention paper develops a near linear time algorithm for attention under the mildest assumptions on the attention metrics that we could have come up with. And the general idea, actually David Woodruff will give a talk about this later in the afternoon, so I'll just say a couple of words and advertise for his talk. So the idea is that if you get rid of heavy hitters and then do a block diagonalization of the remaining metrics using, for example, a sorting LSH technique, you can have an implementation. So first of all, like after getting rid of block like heavy hitters, the matrix is block diagonalizable, and in practice we see that that's like a good assumption to make. And this makes like basically the assumption of getting a linear function, like linear attention. Basically the assumption is after removing those, the condition number, or basically the stable rank of the remaining matrix should be small. And the running time is a function of that variable. So like David will talk more about this. But there also we make some assumptions on the metric, on the attention metrics. And in practice, it's a good gameplay when you want to fine-tune your network and improve inference time and like serving time. So there is a quality hit here, but there is a good trade-off in quality hit. And Palin just arrived very much on time because he just planned for it. So the next attempt was to see if we can relax the softmax function and get a linear time attention. So it turns out that if we change the softmax function in the attention metrics to a polynomial function, then the sketching problem becomes much easier because we can apply the tensor sketch for polynomials here. And that gives us actually a provably linear time algorithm without any extra assumption. So we can approximate the polynomial function like provably. So that on its own has quality hit, But then when you apply like local attention on top of it and some learn sketch function on top of it, we can actually now make it work like in a way that does not lose anything in the quality, perplexity quality. Actually, it improves perplexity quality, and it improves the training time by like 2 to 4x speed up for 32 context length. And as we increase the context length, the trade-off and the improvement improves. So I guess I really have to stop, or maybe. So yeah, like the general idea, and like you can talk to Pelly more, is first of all to use, you know, like so like the first thing to observe is that if we change the softmax to a polynomial without making the assumption, without sketching it, if we go to a polynomial of degree 4 or like 6, let's say 8, we don't have any loss in the basically perplexity, but then we have to sketch it as well. And like the moment that you sketch it, you lose, but then you gain back by local attention. And yeah, like the technique is based on the tensor sketch. Here, maybe I can, yeah, like, so one important thing that I want to emphasize here is that when you want to generate also the next token, do I have that slide? Yes. Yes. The next token generation for polynomial function is also constant. So the big improvement here, moving from softmax to polynomial attention here, is that the next token generation is actually constant, and we can implement it by changing the order of computation. We have some open problems here. I am happy to share this slide with interested audience. And like this is Pranis and Pelin, who know there is like room for improvement here, and there's good theoretical sketching problem for this workshop. I guess I have to wrap up. Yeah, I guess the story is that algorithm, we still matter. First of all, like optimization, larger scale algorithms and so on have a big place in optimizing this new area. And data efficiency is, to me, like the most important thing that we can contribute to from a sketching type algorithm, and like from a scalable type algorithm. Like this is one place that we can contribute a lot. Also on the retrieval side, when we have retrieval augmented generation, if it's called like for graph RAGs or like for efficient RAGs, these are like important topics. There's also like the topic of understanding which like type of algorithms, like specifically graph type algorithms, LLMs can solve or not. We have a paper on arXiv about this, and that's also like a topic of interest that we can actually discuss at some point. The reason that I highlighted here is that we make some connections between the reasoning capability of, do I have a slide about that? Yeah, we do. So we make some connections between the reasoning capability of transformers and the massively parallel computation model, which is very closely related to the topic of this workshop. And I'm trying to encourage more folks to think about the relation of transformers and like what they can do, what type of problems they can solve, and like the MPC model. It's also interesting to observe what type of graph algorithmic problems can be solved, like cycle check, connectivity, edge count, node count, like with what type of transformers or with what length. Or like, for example, what we observe is that for some problems, you need at least logarithmic length, depths, and so on and so forth. So I guess I'm going to wrap up now. Thank you.
So if you had to say like a key takeaway message, that we can all kind of remember concisely, what would you say is something important to keep in mind?
I guess like try to work on these areas in this order of importance, I would say. This order of importance. Thank you.
Any other questions? Okay, now let's thank Vahab again.
Hello.
Our next speaker is Anshuman Srivastava. So it's a pleasure to have him here because I've been following a lot of his